just set it up later. So after when I hit the so not yet. Okay. Not yet. Just keep it connected. Yeah, leave it open.
It's almost there. I need new figures, and leaving figures is the worst part of like any paper, especially since I'm like basing it on my master's thesis, so I already have figures. I can't use them.
Does it show backwards so like mirrored or
yeah?
But you can flip it.
When it uploads, it will be fine.
Oh,
yeah. I think. I'm assuming that if someone must have seen one of the videos and they would have found out that it's the other way around. So I think we got everyone. We can probably get started. Good morning. Hey, good to see you again. All right, today is going to be the last discussion on some of the boilerplate stuff for vector calculus and the tools that we're going to need to describe fluid mechanics and analyze fluid flows. Last time we finished off with some of the vector stuff, with the scalar product and the vector product between vectors, etc. Now it's time to actually look at rates of change. And that's where the words calculus comes from, is, we look at infinitesimal changes in things. And you will notice that throughout the most of your engineering career, and as you study physical phenomena, it is easier to describe rates of change of things rather than things themselves. Because typically the laws of the universe, the great conservation laws that we will learn about, they just are easier to describe in terms of rate of change, because you don't have to have knowledge of the initial size and property of the system. All you could say is the rate of change of the population is that much, whatever the population is, right? Whether it starts with 2 individuals or 10 billion, for example. So the rate of change tells you how that population is changing. And so looking at vector rates of change of vectors and rates of change applied to vectors is going to be really important as we describe fluids, okay? So first, we're going to look at the gradient operator, okay? So gradient of a scalar, okay? And that is given as, okay. Now, this symbol, many of you call it del phi, okay? This symbol del, phi is the scalar. It's just a scalar quantity, like the pressure, the temperature. Again, it's a field. So phi is phi of x, y, z, and t. This one, some of you might call it del. I really don't like that nomenclature, but that's fine. The actual name of that symbol is Nabla, okay? The name of the symbol is Nabla, okay? The way I describe this, I say this is grad phi. So you might see in papers, textbooks, in the exam, you might see both of those used interchangeably. Okay? Now, this operator, Nabla, we call this an operator, okay? And it's related to the derivative. Just like in one dimension, you would say, df by dx, In many dimensions, let's stick with 3 dimensions, you can define Nabla as a vector itself, but it's an operation vector. D by dx, d by dy, and d by dz. You need partial derivatives because Nabla operates on fields, okay, that cover all space dimensions, x, y, and z, okay? And if you think about it, here is just a vector. You can add an arrow on it, you know, that's fine. You can use an arrow or not, but it's implicitly understood that Nabla is a vector. It has these 3 components, but those are operators, okay? There's nothing in here yet. We have yet to fill in the gaps over here. So when you say Nabla phi, this is saying d by dx, d by dy, d by dz applied on phi, which is equal to d phi by dx plus d phi by dyj plus d phi by dzk. Phi could be anything, could be pressure, temperature, etc. Okay. The gradient of a scalar results in a vector. So grad phi is a vector. Grad phi or Nabla phi, either nomenclature, it's a vector. Okay. We always say the gradient of a scalar. We will later define the gradient of a vector, but that becomes, you know, turns into tensor, etc. But as far as we need to understand now, we're looking at gradients of scalars. It results in a vector. In a way, the gradient operator upgrades the scalar, okay, to 3 dimensions or n dimensions, you know. Okay, but what do we mean by a gradient? Again, I like the intuitive understanding. What does a gradient tell you? What does grad phi tell you? Let's suppose you have some quantity, you know, you have a fluid flow again in 2D, and you have like high pressure over here. P is high over here. And then as you go down the pipe, you have P is low over here. Okay. What does the pressure gradient tell us about a quantity? What does it indicate? Pardon me? Do you see any time dependence over here? So the gradient, strictly speaking, is a spatial operation. The operation on time is just a single derivative. It doesn't result in a vector. So what you're saying is d phi by dt, that's if you apply d by dt to a scalar, it's going to be a scalar. If you apply it to a vector, it's going to be a vector. We're specifically talking about gradients. So it's really change over space, but what does it mean intuitively? You had no idea?
I want to say that it changed based on the direction. We can say, for example, the pressure in x direction can change by the around the phi, around p delta x.
Okay, so you're on the right track. The gradient of a scalar tells us something important about where things are high and where things are low. So if you take the gradient of the pressure, I'm going to show you now, I'm going to help you guide me understand that. It's going to tell us where the pressure is high and where it is low, depending on the grade. So let's look at a 1D example. In 1 dimensions, the gradient really degenerates to a single derivative, okay? In 1 dimension, okay, gradient of f of x is really df by dxi, which is identical to the total derivative df by dxi. So let's take an example. I'm going to look at, have a little Gaussian function over here. I'm going to look at the function f of x equal, you can try this at home, e to the minus x squared. Okay, that function is just your standard bell curve. Okay, gonna look something like this. Okay, so this is f of x. Okay, just put this x, and this is f of x over here. Okay, we agree on that. Okay. Now, grad of f of x is equal to df by dxi, which is minus 2x e to the minus x squared. Okay. Now, I'm going to plot this for you. What this looks like is what this grad f looks like. It's going to start like this over here. It's going to go up, and then it's going to kind of go down. Then it's going to do this. Okay. What is this telling us? As we are approaching the peak of f of x, the gradient is positive. Okay, the gradient is positive. And over here, as we are going away from, so imagine you're riding on this bell curve. Okay, so imagine that's me, and this is my blazer. Okay, only have a blue blazer, so I have to wear it with my black jeans, with my khaki pants, with everything. So, so that's my blue blazer. Okay, and I'm riding on this. As I'm going up, my gradient is positive, right? It's a positive value. Okay, and and then as I reach the peak, the value decreases and goes to 0. Okay, and then as I'm leaving the peak, my gradient is negative. Okay, now assign almost like a direction to this one. What this is telling me is that as I'm approaching the peak, my gradient is higher, and as I'm leaving the peak, my gradient is negative. Okay, what this is telling us really is that the gradient always tells you where the peak is, always points in the direction of the peak. So when you are over here and you're moving in the plus x, because that's our reference, plus x plus y, right? If you are over here, it tells you that, hey, the peak is over there. Is over there, right? It's positive. It's telling us it's in that direction. But when you are over here, you get a negative I. It tells you that the peak is, as you are leaving here, tells you the peak is in the opposite direction. So this vector df by dxi, it looks like this. It's positive and then gets smaller. And over here, it's negative, okay, and gets smaller, right? So it's always pointing in the direction where the peak is. Really, so if you plot this thing, if you plot the direction, over here, this is all positive, and over here, it's all negative. So they're negative I, positive I, okay? So this is grad f of x. This is very important because this tells us, specifically in fluid mechanics, when you look at the gradient of the pressure, the gradient always points in the direction of the higher pressure, okay? So in a pipe flow, in a 1D pipe flow, assume you have a high P over here, low P. dP by dx is P exit approximately minus P at the inlet over the distance, okay? If P exit is lower than P inlet, then this is a negative quantity. So dP by dx in the pipe is negative, therefore, it points in this direction, always towards the inlet. Tells us that the higher pressure is at the inlet. But how come the flow goes from left to right? Because you will see later the equations have a negative sign in front of dP by dx. So it flips that sign. But the pressure gradient itself, or the gradient of the scalar itself, always points in the high direction, okay? I'm gonna give you now a two-dimensional example. Okay, actually, I think I can, okay, system power. Power on, PGA. So in 2D, it's harder to visualize that, and 3D even harder. Okay, but that's why we do what we call these projection plots and these 2D vector plots. Let's see if I can turn this off. Is this good? See? Oh, it's not connected. It's like you're holding a camera and you think you're recording, your kid's birthday, and then you forgot to press that red button. Now on your phone, it's gosh. Okay. Can you all see? Okay, this is a little Python code. Uh-oh. Okay, so this is the curve that we just looked at, e to the minus x squared and the derivative. Okay, but I want to go to the more exciting example. This is a two-dimensional function. Okay, it is x e to the minus x squared plus y squared. It's shown over here. Okay, in 3D it looks like this. Okay, so you can see there's a little valley over here, and there's a peak over there. Okay, and this is let's say positive x, positive y, and positive z. Now, when you take the gradient of this function, this is a scalar field, two-dimensional. Okay, what are we going to expect from what we learned? What are we going to expect the gradient to tell us? So think of the gradient as a vector. How do you think the vectors are going to look like? So if you're over here, closer to the valley, they're going to point to the peak, right? So all the vectors are going to be pointing all the way towards the peak. What about here? If you're over here, they're also going to all be pointing to the peak, right? Okay, this is exactly what happens. And I have this code down here showing you this. Okay, these arrows here are the gradient of that function. Okay, this is think of it as a top view of that surface we saw above. This is the valley, this is the peak. Anywhere you are in the valley, you're like, no, this is low, go out. The way out, pointing away from it. Now, the fact that these vectors are pointing in that direction tells you that there's another peak over there, okay? But at least if you focus on this peak, look, they're telling you, hey, if you go over here, this is where the peak is. Just go in this direction. And then you approach the peak, they're all pointing towards the peak, okay? This is pretty cool, right? And gradients are critical in determining where maxima and minima are. And you know this from one dimensions. How do you find a maximum or a minimum? You set df by dx equal to 0 because the derivative tells you where the peak is. And right at the peak, the derivative is going to be 0. But derivatives are indicators of where the maximum is. In optimization, in constraint optimization, when you take a course with Professor Powell, you're going to use the gradient to find the direction of where the peak is, okay? If you're trying to maximize or minimize, you're going to use the gradient to do that. All right? Okay, I hope this was helpful. Use hand sanitizer after. Okay. All right, so now we're done with a gradient, okay? Gradient of a scalar, right? So now we're going to look at the divergence of a vector field. So the gradient of a scalar upgraded a scalar to a vector. Now the divergence is going to take a vector and downgrade it to a scalar. Not that there's anything wrong with a scalar, upgrade, downgrade is just an ordering of things like, one-dimensional quantity, n-dimensional quantity, tensors are higher order than vectors, etc. So that's what I mean by downgrade or upgrade. I have nothing against scalars. I respect them a lot, and I think they're very useful. So, okay. So now, if you think, I want you really to keep in your mind the idea that Nabla is a vector itself, in and of itself. There's a quantity that you can form. It's called the divergence of a vector. Let's call it A. Let's call it U. Okay. So this is just a scalar product, right? Like A dot B, correct? It's just using the Nabla operator. What does that result in? D by dx, d by dy, and d by dz dotted with u1, u2, u3. What does that give you? Just a simple dot product, right? So du1 by dx plus du2 by dy plus du3 by dz. Would help me if you check my algebra because you can see the big picture. I cannot see it. So is this correct? Okay. And this is a scalar quantity. Okay. So who wants to guess what my next question is going to be? Pardon me. A what? Vector product? No. What is my next question going to be? The meaning, yes. Okay, what do we mean by the divergence of a vector field? Does anyone have any clue? Have you seen the divergence before in your classes? You have. Okay. Do you know what it means?
Net outflow
Net outflow of.
the
Okay. So why?
it gives the impression of the fluxes
Okay.
generated from the surface current.
Okay. So you're right. What Afiz is saying is that the divergence measures how much vector is leaving a point. Okay, how much vector is leaving a point. And that's correct. But let me kind of elaborate on that. So first of all, think of all, let me put it in capital, all vectors as a fluid flow. Right? It kind of, when you plot a vector field, it looks like there's flow going along those vectors. So it's an absolutely great way to think about vectors. The divergence, div u, is actually not defined like that. The definition, a rigorous definition of the vector field, of the divergence, so a definition of divergence is div u is equal, I'm going to write it and then we'll discuss it. Okay. Over S. If you were, before I look at this definition, if you were to look at a bunch of, vectors, etc., and you take a little region, a little volume, anywhere in that fluid, anywhere in that vector field, you draw that region, it has a surface area S and it has a volume V. Okay. If you take the integral, what is the integral of u dot n? So first, what is u dot n? N is the outward unit normal of the surface. So anywhere here over the surface, we have these little n's over here, right, pointing out. Okay. This is n. I'm gonna change my vectors over here a little bit like this. So along that surface, some vectors are going into the surface, are crossing it inwards, and some vectors are leaving it. So if this is a surface and this is the vector n, and this is u, okay, over here, u dot n is positive, correct? Because they're both pointing the same direction. And we kind of saw what this dot product tells us. So u dot n is just telling us how much u is kind of in the direction, how much u and n are pointing in the same direction. If they are, then it's positive. The other situation is when u is coming in and n is outward. In this case, u dot n is negative. Okay. Now this integral over here, over this entire surface, what it's doing is just simply summing up all the u dot n's along that surface. If you have more positive u dot n, then this whole integral is going to be positive. If you have a larger amount of positive u dot n than a negative u dot n, then this integral is going to be positive, correct? So integral of u dot n ds is positive if flow is mostly out of surface. And it is negative if flow is mostly into surface. Agreed? Makes sense? Now, what this definition is saying, take this volume now and shrink it all the way to a single point. And divide by the volume. So the volume is approaching 0, and the integral is also kind of approaching 0, or it's a finite value. It turns out that this whole thing has a finite value. But the sign is the same as we described over here. So div u will be positive if flow is leaving point and negative otherwise. Of course, it can be 0 as well if there's leaving, if okay, not otherwise, if flow is entering, and 0, no net flow. So whatever is coming in is leaving. This case equals 0. Give you a moment to think about that. So, Louise, did you have a question? Okay. I thought you raised your hand, but okay. So div u is identical to the sign of this integral. The sign of div u is identical to the sign of this integral. Measure of, at that point, is there more flow leaving? So if you draw like a little volume, is there more flow leaving than entering? If so, that's positive. Is there more flow coming into, converging into the point than leaving? Then it is negative, okay? And 0 if you have the same amount of flow coming in and leaving, okay? Now this is important. This last point is very important, okay? So if you open your faucet, so you measure the flow rate at the faucet, you put a hose on it, and go measure the flow rate at the end of the hose. What do you expect to see? So just assume you measure, 4 gallons per minute at the faucet. What do you expect to measure at the end of the hose? 4 gallons per minute, right? So what this means over that hose is that div u is 0. Whatever is coming into the hose is going to leave. So that's how we're going to tie this into fluid mechanics. This condition, div u equals 0, turns out to be the condition for incompressibility. And you already have a physical understanding of this. All right, let's now test your knowledge if you were following with me. I want you to form into your famous groups. And now I also want you to pick a name for your group. The funnier it is, the less likely I will pick you. Okay? So I want you to come up with really hilarious names for your groups. Okay? And I'm going to ask a question, and as a group, you're going to discuss it. And I will randomly pick a group name, okay? And the spokesperson for the group. Yeah, and the funnier your group name is, it means less likely I'm gonna pick you. So have at it. You should see the names in my numerical methods class. Very funny. Yeah, and if you can write your group name on a little sheet of paper, okay, you're gonna come out of this class with like a stack of papers. Sam is like, this class is gonna cost me a ton in papers. I haven't been using papers in years. All right, okay. So while you pick names, I'm gonna draw some things on the board. Okay. I'm gonna ask you, what is the sign of? By the way, div u is also written as div u. So the way I used to describe this term, I say either nabla dot u or divergence of u or div u. Okay, all of those are equivalent. All right. If you want to come up with a name for your team, please, and put it up. I am serious. Okay. 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 All right. So now I want you to form into those groups, pick up a name, and let's see, we got the first name.
We're the gamer gang.
Gamer Gang. Okay. All right, Gamer Gang. Your question is going to be, I want you to tell me what the sign of div u is for the following scenarios. I want to know what the sign of div u at this point is. All of the arrows represent the vector u, and the sizes are to scale. Okay. So in this case, for example, these vectors are smaller in magnitude than those vectors. Okay. Same here. Those guys are larger than these guys. These guys are same, equal length. Same here. Same here. Okay. Alien. Passat. Divergence dudes. The fighting non-gooses? Mongooses. I'm not gonna pick you. Victor. You're okay then. Hey, why don't you team up with them? Yeah? All right. Okay. All right. Who would like to take? Oh, there's still a group working. Okay. Go on, be loud and talk. If the net flow into the point, if there is net flow into the point, then div u is negative. If there's net flow out of the point, then div u is positive. And if there's no net flow, then div u is 0. Okay? Draw a surface around the point. Think of a little surface around the point, right?
Okay.
Yeah, but like at this point,
Uh-huh.
there is, let's say there's 1 gallon per minute coming in,
Uh-huh.
but there's like 10 gallons per minute leaving, right?
Right.
So what is the net in that case?
Coming out.
Yeah, exactly. Think of it intuitively, okay?
Big things.
Oh, no.
Discuss it with each other. If one of you figured it out, please discuss it with your teammate, okay? All right. Who wants to take the first one? All right, divergence, dude. There's a net flow going into that point, right? So div u over here, div u is negative. Okay. What about this case? Alien? Positive. Why? Okay. So here, net flow in, net flow out. All right. You want to take it? Positive. Why? Yep. Div u is positive because the net flow around that point is out. We will explain later how this is possible. For compressible flows, this is entirely possible. You can compress the fluid and pack more of it and send out more at that point. So there might be something going on at that point, like a reaction rate that is just generating somehow more mass, okay, and sending out more fluid out of that, away from that point. Over here, Passat, negative, why? In, yep, net flow is in. Okay. Degenerate case, 0, yes. Why? Yep, net flow. So whatever is coming in is leaving. So these guys are coming in, right? These guys are coming in. Those guys are leaving the same amount. Okay, net flow is 0. Excellent. Who thinks this is a cool way of thinking of divergence, right? Yeah, intuition. This is going to be really important for those doing computational fluid dynamics later, because this div u is going to also tell you, and we will learn that later, whether the pressure is going to be high or low. Okay, if the flow tends in an incompressible flow, and again, I'm jumping the gun here, but just to kind of think about it intuitively, in an incompressible flow, you cannot pack fluid particles together. They're going to want to resist. Okay, so if the view is trying to be positive, what happens? The pressure is going to come in and tell them, no, 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 no. You're going to stay right there. Okay, so the pressure increases. And if div u is negative, then the pressure, so that tells you about the pressure gradient, where what direction it's pointing. So in this case, there's going to be a higher pressure away from this because it's trying to push it down. In this case, it's going to be the opposite. Okay, so it tells you about the pressure gradient. Pressure and mass are tightly related in incompressible flows in particular. Okay, anyway. All right, last couple of items. Well, there's still a few. I don't think I can cover all of them today, but we'll take a few minutes out of next lecture. Okay, now we're going to talk about combining operations. We're going to talk about the Laplacian operator. Laplacian. And the Laplacian is, you probably know and say this is del squared phi. But really, the way I like to think about it, it is the divergence of the gradient of a scalar. Okay? Div of grad phi. Now, when you think about it, is this a scalar or is the result a scalar or a vector? Scalar. Why? Yeah. So think of this as vector A dot vector B. Agreed? And the result of that is just simply the dot product, which is a scalar. So how do you find out the constituents of this quantity? Just write it out. D by dx, D by dy, and D by dz applied, so dotted with D by dx, D by dy, D by dz applied to phi, so you just put in phi over here. Just take the dot product. Gives you d2 phi by dx squared plus d2 phi by dy squared plus d2 phi by dz squared. Okay? Okay, what is my next question? What does this mean? What does this mean? Okay, I want you to think of it this way. Now you know what gradient alone means and what divergence means, right? Now you're stacking divergence on top of a gradient. So can you try to combine what we described? So the gradient always points in the direction of the highest value, okay? Always points in the direction of the highest value. The divergence tells you if things are coming in or leaving. So when you combine the two, what does that tell you? Give it a thought. Pardon me?
Convergence? It's convergence.
Convergence, what do you mean by that?
Like, the divergence of that is somebody coming out, they point to the direction of peak,
Mhm.
point to the direction of comes to the
Okay, so how can I use this in practice, for example? So if the Laplacian is positive, negative, or equal to 0, how does that help me? Pardon me? What was it? I'm sorry, I can't tell who is speaking because of the masks. Yeah. Acceleration. I don't know. How is it acceleration?
For example, like, I just think, for example, like a divergence or gradient, it can represent like
I see you're thinking of a derivative on top of a derivative. Yeah, but there's no time involved. So you might be describing describing the slope of the curve. So okay, jump to 1D. What does the second derivative tell you in 1 dimension? The what?
If it's a maximum
Or a minimum. Well, the first derivative tells you that, but the second derivative tells you if it's concave up or concave down, right? Okay. So the first derivative, the gradient, tells you where the maximum and minimum is. Okay. But the second derivative, or when you apply the divergence on it, tells you how big of a minimum and how big of a maximum this is. In other words, is this going to be a local minimum or a global minimum? A local maximum or a global maximum? Okay, how big your maximum is. Okay, so yeah, let me elaborate this a little bit here. Yeah, so it does tell you how large a min or a max you are at, just like the second derivative in 1 dimension tells you, the first derivative tells you if you're at a extremum, right? Whether, max or min, but the second derivative tells you, yeah, the concavity, right? If it's a min or max. In more dimensions, it's gonna tell you how big of a min and how big of how big of a max, how low of a min, and etc. So it's an indication of how deep your valley and how high your mountain is. Okay, the Laplacian. Okay, there is an operation that I have to define, and it's called a dyadic operation. We will use this a few times, but I just want you to Just know how to do it, okay? And it's strictly a bookkeeping convenience. Doesn't really have any important mathematical significance for fluid flow. But oftentimes we will see that we're going to stack two vectors next to each other. Just write them like this, AB. Just write them like this. Why does this show up? We'll see later, okay? But I just want you to know how to do this now. And this is called a vector dyadic, okay? Vector dyadic. So this will show up later when we do grad U. So it's the gradient of a vector, okay? And you need to be able to define that. But if you apply just this little trick, little formula, your life is going to be easy. No need to use tensors or any of that. So the way I write this is AB, I define it as A, and I use this operator for the dyadic. It's not a product. It's just stacking two vectors next to each other. Now I want to convert this to matrix algebra because we know how to multiply matrices with each other. So I'm going to write this as the matrix U, which is just a column vector, really, times the transpose. So this is strictly vector multiplication. Vector A times the transpose of vector B. Yeah, let me put it this way. Okay, so in other words, A is a column vector. So A1, A2, A3. And the transpose of B is B1, B2, B3. So we converted this vector dyadic into an operation that we know how to do in terms of matrices. It's just the product of two matrices. So I'm representing the vector as a column vector, but I'm representing it as a 3x1 matrix. Okay. So for this matrix product, this is 3x1 times 1/3. It's going to result in a 3x3 matrix, or it really is just a tensor. You should know how to carry this operation. Okay. So what you would do you know how to do it? I forgot. Okay. So you take the first row and the first column, second row, first column, third row, third column, and so on. Third row, first column, and then you continue. So you get A1. So for this point, it's the first row and the first column here. So you get A1, B1. For this point is the second row, first column. Pardon me. And then A3, B1. Same thing over here. You get A1, B2. So you get the first row, second column, and then A2, B2, and then A3, B2. And then the third one is A1, B3, A2, B3, and then A3, B3. Okay. So now go back into your groups and do grad U. To help you, grad is d by dx, d by dy, and d by dz. And u is, write it u1, u2, u3. Go ahead. Again, this is going to be strictly bookkeeping. Once we write all the governing equations, we're going to write 3 equations, 1 equation for each direction. But then we're going to say, you know what? It would be much easier if we write all of those equations in one vector, for one vector equation. And then you're going to find out that you're going to get that gradient of the velocity vector field.
I know, I'm a little upset too.
Limited buffer bracket.
This is so cool. I want to get one of those stylus.
Yeah, it's so nice.
Is it as responsive as just writing on a? Oh, cool. And can you lean your hand on it? Yeah. Yeah. Nice. All right. Looks like most of you got it. The victors on the in the back. Do you think you know how to do it? Yeah. Okay. Do you feel comfortable? Pardon me. Do you feel comfortable going up on the board? Oh, do you want to say it? Okay. Okay, go ahead. So we're going to start with the first column. du1 by dx. du2 by du1 by dy. Yeah. du3 by dz. Does anyone agree? Disagree? No? 1, 1, 1. Okay. So it's du1, du1. And then, so really this is 1. This is 2. So you get du2, du2, du2. And then this is 3, right? du3, du3, du3. And then this is x, y, and z, right? dx, dy, dz, dx, dy, then dz. Now, what is each column? I'm gonna tell you, it's the grad of yes, u1, u1, grad u1, grad u2, and grad u3. Agreed? Yeah, this is just a vector. You can define a vector, gradient of u1. That's it. Gradient of u2, gradient of u3. Strictly bookkeeping, okay? No need to worry about what it means. We're gonna derive the equations in numerous ways. It just looks like we're gonna see this term show up. It's gonna simplify our math a lot. All right, I have 2 minutes. I think I can do. Okay, so now let's define we will also be dealing with the Laplacian of a vector. That one is simple. So we can define also Laplacian of vector. We get del squared u. Now you can do this as div of grad u, okay? Or you can just do this as del squared of u and apply the Laplacian on each individual component, okay? So in other words, what you do, you say that this is d2u vector by dx squared plus d2u vector by dy squared plus d2u vector by dz squared, okay? So this one is going to have ijk components, ijk and ijk. So this one will be d2u1 by dx squared I plus d2u2 by dx squared j, correct? You're applying the second derivative on the entire vector, okay? Plus d2u3 by dx squared k, agreed? Because u is u1i plus u2j plus u3k, right? It's just a lot of bookkeeping. Plus d2u1 by dy squared I plus d2u2 by dy squared j plus d2u3 by dy squared k plus d2u1 by dz squared I plus d2u2 by dz squared j plus d2u3 by dz squared k. Now you have the three components of the resulting vector. This is the ith component. It's del squared u1. So in other words, this is equal to del squared u1i plus del squared u2j plus del squared u3k. Okay. Bookkeeping, you're gonna refer to those later. We're gonna typeset a little cheat sheet for you. Okay. So you can use it in your exams and homework and in your life. All right. Thank you, everyone. I will see you on Wednesday. All right.